ChatGPT knows a lot, but it doesn't know your data. It can't read your company's documents, search your internal wiki, or answer questions about your proprietary systems until you add RAG. Retrieval Augmented Generation is how you give AI access to your own knowledge base without retraining the model. It's how companies build customer support bots that actually know their products, documentation assistants that search internal wikis, and research tools that cite specific sources. In this video, you'll understand exactly how RAG works and why it's become the standard approach for enterprise AI applications. Let's understand the problem RAG solves. Large language models are trained on public data up to a certain date. GPT-4's training data ends in 2023. It doesn't know about events after that, company-specific information, or private documents. You could fine-tune the model on your data, but that's expensive, takes time, and requires retraining whenever your data changes. Fine-tuning also bakes knowledge into model weights, which means the model might not distinguish between your data and its general training. RAG takes a different approach. Instead of teaching the model your data permanently, you retrieve relevant information at query time and include it in the prompt. The model reads your data as context and generates responses based on it. This is dynamic, up-to-date, and doesn't require any model modification. Think of it like an open book exam versus memorizing everything. RAG gives the model a reference book. Here's how RAG works, step by step. First, you prepare your documents. Take your PDFs, Word docs, web pages, or database records and break them into smaller chunks. Each chunk might be a paragraph or a few hundred tokens. Store these chunks in a special database. Second, when a user asks a question, you convert that question into a numerical representation called an embedding. This embedding captures the semantic meaning of the query as a vector of numbers. Third, you search your chunk database for the most similar embeddings. These are the chunks most likely to contain relevant information. The search uses mathematical similarity, usually cosine similarity, to find matches. Fourth, you take the top chunks, say 3 to 5 of them, and add them to the prompt as context. The prompt might say, based on the following information, answer the user's question, then include the chunks. Fifth, the LLM reads the context and generates an answer that incorporates your specific data. The response is grounded in your documents, not just the model's general knowledge. Embeddings are the key to RAG. They're how you make text searchable by meaning, not just keywords. An embedding model converts text into a vector, a list of numbers representing semantic meaning. Similar texts have similar vectors. The sentence, "I love pizza," might become a vector of 1536 numbers. "Pizza is my favorite food" would have a very similar vector because the meaning is close. "The weather is nice" would have a very different vector. Popular embedding models include OpenAI's Text Embedding 3, Cohere's Embed, and open source options like E5 and BGE. When you prepare your documents, you run each chunk through the embedding model. When a query comes in, you embed the query too. Then, you compare the query vector against all chunk vectors using cosine similarity. The chunks with the highest similarity scores are your search results. This semantic search is much more powerful than keyword matching. It understands that cancel subscription and stop my membership mean the same. You need a vector database to store and search embeddings efficiently. Regular databases are designed for exact matches or simple filters. Vector databases are optimized for similarity search across millions of vectors. Popular options include Pinecone, which is fully managed and easy to use, Weaviate, which is open source with hybrid search, Chroma, which is lightweight and great for development, Qdrant, which focuses on performance, and pgvector, which adds vector search to PostgreSQL. For production, managed services like Pinecone handle scaling and infrastructure. For learning and prototyping, Chroma runs locally with just a few lines of Python. The basic workflow is create a collection, add your documents with their embeddings, and query by embedding to get similar results. Most vector databases also support metadata filtering. You can search for relevant chunks that also match specific categories, dates, or user permissions. This combination of semantic search and How you chunk your documents matters more than you might think. Too small and chunks lack context. Too large and you waste token space on irrelevant information. A common starting point is 500 to 1000 characters per chunk with some overlap between chunks. Overlap ensures that sentences at chunk boundaries aren't cut off from their context. Fixed size chunking is simple but naive. Better approaches consider document structure, split on paragraph breaks, headers, or section boundaries. For code, split on function or class definitions. For conversations, keep question-answer pairs together. Semantic chunking groups related sentences together based on embedding similarity. As you read through a document, start a new chunk when the topic shifts significantly. More advanced techniques include parent document retrieval, where you embed smaller chunks but retrieve the larger parent document for context, or multi-vector retrieval, where you create multiple embeddings per chunk for different aspects of the content. Basic RAG works, but there are many ways to improve it. Re-ranking is the first optimization. Your initial vector search returns candidates quickly but imprecisely. A re-ranking model like Cohere Re-rank scores those candidates more carefully and reorders them. The top results after re-ranking are usually more relevant. Hybrid search combines semantic search with keyword search. Some queries work better with exact keyword matches, especially for names, codes, or specific terms. Hybrid search gets the best of both approaches. Query transformation improves search by reformulating the user's question. You might expand abbreviations, add synonyms, or break complex questions into subqueries. Hide, hypothetical document embeddings, generates a hypothetical answer and searches for documents similar to that answer. Metadata filtering narrows search to relevant subsets before semantic matching. Filter by document type, recency, department, or user access level. These optimizations can dramatically improve RAG quality but add complexity. Start with basic RAG, measure performance, and add optimizations where they help most. Let's look at real-world RAG applications. Customer support bots use RAG to search product documentation, FAQs, and past support tickets. When a customer asks about returns, the system retrieves the return policy and any relevant edge cases. Documentation assistants help employees search internal wikis, policies, and procedures. Instead of navigating complex folder structures, users ask questions naturally. Legal research tools search case law, contracts, and regulations. Lawyers describe what they need, and the system finds relevant precedents with citations. Code assistants use RAG to search code bases and documentation. Ask how authentication works in this project, and it retrieves the relevant code files and design docs. Research platforms search scientific papers, internal reports, or market analysis. Analysts ask questions and get answers grounded in specific sources they can verify. In all these cases, RAG provides two key benefits: access to specialized knowledge the model wasn't trained on. RAG is the bridge between general AI capabilities and your specific data. You now understand the core concepts: chunking documents, creating embeddings, vector search, and augmented generation. Start with a simple implementation using Chroma or Pinecone for the vector store and OpenAI or Anthropic for the LLM. Test with your own documents and iterate on chunk size and retrieval parameters. For production systems, add evaluation metrics. Track retrieval precision, answer quality, and user satisfaction. Consider the trade-offs between speed, cost, and accuracy. Common next steps include adding more advanced chunking strategies, implementing hybrid search, and building feedback loops to improve over time. In the next video, we'll explore AI coding assistants and how tools like GitHub Copilot, Cursor, and Claude Code use these same principles to help developers write better code faster. Subscribe to keep learning, and I'll see you in the next one.